This is a week 3, problem number 2. It's about the effective nuclear charge. So effective nuclear charge has a symbol of Z effective, and you have to know how many what's the number of proton in the nucleus. So let's read the problem. Calculate Z effective experienced by one valence electron of chlorine and aluminum. So let's think about chlorine first. So chlorine, if you look at this periodic table, chlorine is right there. There is a 17 electrons. So it has a 17 electrons. So you have a 17 proton in the middle. And then if I start to draw the first shell, you have 2 electrons. Right? In the second shell, which is 2 electrons right here. The second shell, 1, 2, 3, 4, 5, 6, 7, 8. Right? So this is an 8 electron, 2, 3, 4, 5, 6, 7, 8. So those are the 8 electrons. 2 electrons first. And so you come to about the neon so far. So and let me change the color a little bit. So this is now you have here 1, 2, 3, 4, 5, 6, 7. So the third shell, you have 7 electrons, right? 1, 2, 3, 4, 5, 6, 7. And then they are asking for a valence shell electron. So this is a valence electron right there. And how do they feel about it? So this for this valence shell electrons, what they are essentially kind of the feeling, or what they call the nuclear charge shielding, they have 6 valence electrons, and then what they call this on the inside, you have 10 electron as a core electrons, and this is top there is a valence electrons. Okay, and you have 17 electron total, but we are talking about for 1, and this is how they are effective. So I'm counting in a different way. That this is a little bit new to me, the way that it's being counted. And let me show you your textbook that is shown up here. So here I show you the textbook from this Macmillan textbook. And so this is an equation on the Z effective, and you're shown up here. So it's a Z minus S. Z is essentially number of protons in the nucleus, and the S is the shield factors. And if you look at here, and then there is some equations say that if you're looking at the value of 0.35 and 0.85 is the one that they use for the shield number. So the valence electron is 0.0. Valence electron is the one, the shield factor is they contributed to the 0.35 to the number called S, whereas the electron in the lower n value, which is a co-electron, is a 0.85. Okay, so using that, so let's go and let's finish this. Okay, so for the chlorine, right, the Z effective, this is always Z minus S, and I know this is for chlorine, once again that's a 17. But what about the S? S, you have how many? 6 electron valence electron, so it's 1 less than 17, 1 less than 7, because this is you're not counting yourself for this particular valence shell electron to fill. They are 3 extra valence electrons, right? 1 less than what they have in the valence shell, and plus how many core electrons? You have 10 electron in the core. And then what do they say about this? 6 valence electron each contribute to the S by the number of 0.35. And then you have 10, and they contributed to more effective shielding, 0.85. And if you do that, you will get 10.6. Okay, so this is this one goes right there. So therefore, 17 minus 10.6, and that will be the 6.4. So this is an effective mass. So what this means is in the core, the plus 17 is really the Z, but there are electron cloud that are surrounding it. So if actually from the outside, it feels like Z effective, right? Z itself is a 17, but now G effective is only 6.4 for chlorine atom. Okay, so for the case, I guess the textbook is wanted to compare the second case, which is aluminum. So aluminum is this. So for aluminum, the Z effective, same thing here, but now the Z is here is a 13. Okay, so the 13 means you have 13 electrons or 13 proton in the center. But now let's talk about the S. How many valence electrons are talking about here? So okay, let's solve in a different way. Aluminum means essentially neon. Okay, and then 1, 2, 3. So 3s2. 3p1. Okay, so these are the electrons in the valence shell. So, and then you want to looking at a particular valence shell electron to fill it. You have a 2 valence shell electrons extra, right? For this one, and then you have a core electron, which is a 10 core electron. Okay, so so this is a 2 valence electron plus 10 electron in the core, and then the valence electron effective shielding constant is 0.35, and the 10 core electron is 0.85. By doing so, and then you will have 9.2. That's a shielding factor, so this is a 9.2. So overall, for aluminum, the number that you will have, Z minus S, which is a 13 minus 9.2, which is a 3.8. Okay, so that's an effective Z. So therefore, for the aluminum, the effective Z is Z effective is a 3.8. Okay, so now let's compare these numbers here. So for the aluminum, this is for the aluminum. So the chlorine Z effective is as if 6.4 charges in the middle, then pulling the electron that is under this column, this row here, not column, this row here. Whereas for the aluminum, 3.8 is in the middle. So therefore, it is a stronger Z effective nuclear charges pulling the electron more. So these electrons are being pulled closer to do that. So this is a stronger Z effective. So that's why it is a smaller radius. Okay. So why am I saying this is once you calculate the G effective differences, the bigger the G effective differences, the atomic radius, the bigger they are going down within the same valence shell electrons. So this aluminum and chlorines are at the same time, And if I draw it, the aluminum is the G effective is once again, what was the number? 3.8, whereas the chlorine is smaller. So this is like aluminum, and this is a chlorine. Okay, so that's why the size is, when you go moving to this side here, this side is smaller, right? So that's why the chlorine is smaller than aluminum, and we can kind of using the argument about effective nuclear charges.